Snell's Law and the Critical Angle. This video was originally titled Snell's Law and the Prisoner of Azkaban, but apparently that title is already taken. Snell's Law is the relationship we use to determine how much a ray of light is going to get bent when it transfers from, or when it transitions from one medium to a different medium. So anytime we hit a boundary between two different materials, we call that an interface, that boundary between the two materials. Whenever it hits a boundary there, it has the potential to bend one direction or the other. We call this refraction. We know that different colors bend at different amounts. This results in dispersion of light, of different colors of light, which gives us things like the rainbow. But for now, we're going to look at just a single ray of a single color of light hitting a single interface and how that direction of that ray changes as a result. So we get our light passing through one material. We'll call that material 1 here, and it's going to hit this boundary between material 1 and material 2, and we'll find that when it goes into material 2, it doesn't quite travel in the same direction. We have this little bit of a shift. Well, we need to know a few things about these materials and about the directions in order to make predictions about, well, either the materials or the directions. So the first thing we need to know is this property of the material that we call the index of refraction. We use the variable n for that. So we'll say that in material 1, we have n1. In material 2, we have n2 for the index of refraction. Now, as a side note, index of refraction is a way to describe how fast light travels through this material. So in this equation, c is the speed of light in a vacuum, the fastest that light can travel. That'd be 300 million meters per second, roughly. And v is going to be the speed of light through our material. Now, you may not have heard about this before, but light actually does slow down when it goes into a material other than emptiness, empty space. And so how much it slows down depends on the material. Whether it can travel through very well at all depends on the material as well, but the speed that it travels through is going to depend on the material. So for something like glass, for example, glass, depending on the type of glass, has an index of refraction of about 1.5 or 1.6. So that means that light travels about 1.5 or 1.6 times faster in a vacuum than it does through glass. So anyway, back to the idea of refraction and Snell's law. The other thing we need to know about is how this ray of light hits that boundary. And we have this convention where we don't measure an angle relative to the surface, but rather we draw in what we call a normal line. A normal line being a line that's perpendicular to that surface, and it goes right through the spot where that ray of light hits. So we're going to measure an angle right here, and that'll be our theta 1. And we'll measure an angle right here, and that's going to be theta 2. Now you'll notice that the ray of light, it crosses over the interface, it crosses over the boundary between these two materials. It also crosses over the normal line, but theta 1 is different from theta 2. Now, how are they related? That's Snell's law. Snell's law says that n1 times the sine of theta 1 has to be equal to n2 times the sine of theta 2. So if we know one of those or if we know 3 of those values, we can solve for a fourth one, whatever that would be. So n values are pretty well established. If you know what type of material you're dealing with, you could probably just look up the index of refraction for that material and make some predictions about, say, what direction the light's going to go in after it hits the interface. One way that this is used is actually to determine what type of material you're dealing with. Say you're not sure if something is a diamond or is cubic zirconium. Well, we shine a little light at the boundary between air and the mystery material, and we measure some angles there. How does it change direction as it gets? How does that light change direction as it gets to that interface? So we could get values for theta 1 and theta 2. We know the value for index of refraction for air, so we could find the index of refraction for our mystery material and then see whether that measured value is closer to the one for cubic zirconia or closer to the one for a diamond. We determine whether it's cubic zirconium or a diamond. Now in this setup, we have this relationship that while we don't have any numbers, we can discuss the index of refraction of these two materials and how they relate to each other. I see on this that theta 1 is a pretty big value and theta 2 is a pretty small value. So when I do the sine of theta 1, as theta 1 gets bigger, all the way up to 90 degrees, sine of theta is going to increase as well. So if I have theta 1 bigger than theta 2, then sine of theta 1 is bigger than sine of theta 2 as well. Now these two have to be equal. The left side and the right side have to be equal in this equation, as is true in any equation, of course. So if sine of theta 1 is bigger than sine of theta 2, then n1 must be smaller than n2. So n1 must be smaller. That means we're going from a less optically dense material to a more optically dense material. Optically dense here referring to how easily the light travels through or how quickly the light can travel through there. So something that's more optically dense presents more of a challenge for light, and the light has to take more time to travel through that material. So an example of this might be that we start in, say, air, which is not very optically dense or has a very low index of refraction. Light travels pretty quickly through air, almost 300 million meters per second, in fact. So almost the same as in a vacuum. And then this would be a higher index of refraction material, so maybe that's glass or water. Now this is kind of a useful rule to remember, that if we go from a low index of refraction to a high index of refraction, our ray of light starts out pretty far away from the normal line and it gets closer to the normal line. So in this one, if we said n1 is greater than n2, our ray of light is going to bend toward the normal line. Now if the opposite had been true, if n2 were greater than n1, then the ray of light would bend away from the normal. So by bend toward the normal, we just means that it gets closer to a state where it's moving perpendicular to that interface, so closer to the normal line. Now here's an interesting consequence of Snell's law. Let's say our light starts off in this material that's got a higher index of refraction. So it starts off in, oops, I wrote this backward. Let's say n1 is greater than n2. And it's going into this other material. So that light is going to bend away from the normal line. So if I have a ray of light that comes in at some angle like this, it's going to leave at a bigger angle, an angle that's farther away from the normal line. All right, well, what if we come in at a little steeper angle? So we come in like this instead. Well, now our ray of light's going to be even farther away from the normal line. And if we come in at an even steeper angle, like this one, our ray of light would go straight along the interface there. We'd have a 90-degree angle here. That theta on theta 2 would be 90 degrees. Now when we look at the setup for the equation, that's a maximum. n1 sine theta 1 equals n2 sine theta 2. We have a maximum when theta 2 is at 90 degrees. So we can't go any farther than that. If I made theta 1 bigger, which I can do, theta 1 being over here, theta 1, I can still make that one bigger, but the right side of the equation can't get any bigger than that one. So what we find after this point is that our light just stops refracting altogether. It stops leaving the surface completely. Now we haven't talked about this yet, but part of this light doesn't get refracted. It doesn't go through the medium. Instead, it gets reflected. So this green ray, we have a little bit that gets reflected back like this. The red one, we have a little bit that gets reflected like this. And the blue one, we have a little bit that gets reflected like this. And after this angle, which we call our critical angle, theta 1 right there, that'll be our critical angle, the last angle at which light can refract, can escape this glass. After this point, all of our light gets reflected. So theta c is the critical angle measurement that we use. And again, critical angle just means it's the biggest angle from the normal line right here that we can send light in at before we have all of our light get reflected instead of refracted. And so if theta 1 is greater than theta c, we get this state that we call total internal reflection. None of our light escapes. Instead, all of our light stays in that material. So look at a fish tank sometime and get your face really close to the fish tank and look at the boundary between the water and the air. So look up at the surface there, and you'll see this effect from the critical angle. If you look very far away from where you're sitting, you'll see all this reflected light, but you won't be able to see up out of the water anymore. This also gets used in fiber optic technology. As long as we don't bend the fiber optic fibers too much so we don't make the light hit at a very big angle, we don't have any light that leaks out of our material. And so we can send these pulses of light through very long and windy passages of these fibers, these glass fibers, and the light doesn't escape. It just goes straight along that fiber. So we can send information that way. So that's total internal reflection. It happens after we have light going in at the critical angle, and we have Snell's law that informs all that. Thanks very much for watching, folks. If you found this useful, please like it and share it with anybody else you think would find it useful. If you think you'll find anything else of mine useful, please hit the subscribe button. Thanks again.